Summary, BioniChaos turn fetch 0 zirzage. BioniChaos is an open source platform dedicated to democratizing biomedical data processing by offering accessible tools and educational resources. It provides innovative biomedical data processing tools, simulations, and resources for education and research, allowing users to explore and analyze data such as EEG and ECG signals. The platform includes interactive applications like the Cochlear Simulator, eye tracker, and real-time speech visualizer, designed to enhance understanding and engagement with biomedical data. Additionally, BioniChaos maintains a YouTube channel that offers tutorials, live streams, and in-depth discussions to complement its online tools. Cite Turn Search 1. Summary, BioniChaos turn fetch. BioniChaos has recently expanded its suite of biomedical data tools and resources. Notable additions include Graphit, Knowledge Graph Visualizer. This tool extracts entities and relationships from text inputs, generating interactive graphs to visualize their connections, enhancing the exploration of complex information. Turn Fetch Arrow, Cochlear Simulator, an interactive application that visualizes the electrical signals transmitted to the brain by a cochlear implant. Users can adjust parameters to observe different outcomes, deepening their understanding of auditory signal processing. Fetch, a webcam-based eye tracking system enabling users to study gaze patterns, offering valuable insights for user interface design and accessibility improvements. Cite Real-Time Speech Visualizer. This application transcribes spoken words in real time, providing visual feedback on speech characteristics, which is beneficial for speech therapy and language learning. These innovations reflect BioniChaos's dedication to providing interactive, educational tools that make biomedical data analysis more accessible to users. Hey everyone, I'm your friendly robot assistant for today's live stream. I'll be guiding you through the cool stuff we're working on with the real-time speech visualizer. But first, here's a little joke to kick things off. Why did the robot go on a diet? Because it had too many bites. Now that we're all warmed up, let's dive into the live action. I'll be chatting, explaining, and keeping things fun while we develop and play around with the speech visualizer. If you have any questions, feel free to throw them in the chat and let's make this an entertaining session together. Awesome. Glad you're with me. So, let's break down what we're about to explore. The real-time speech visualizer takes everything we say and turns it into visual magic. Think of it like a live show for your voice. You speak, And boom, it gets transcribed and displayed instantly. It's perfect for seeing how speech patterns look, and it can even help with speech therapy or language learning. As I keep talking, you'll see the visualizer light up with each word I say, and the best part? It's running smoothly in your browser with no need for any complicated downloads. That's the beauty of BioniChaos. We keep it simple and interactive. Now let's dive into development. I'm going to tweak a few things on the back end to show how the real-time visualizer works behind the scenes. And don't worry, I'll explain everything as I go so you can follow along and maybe even try this out yourself later on. Got any cool ideas for how to make this even better? Let me know in the chat and we'll have fun bringing them to life. Sure thing. All right, folks, here's where you come in. Feel free to ask me any questions about how this real-time speech visualizer works, or really anything about the tools we're using today. I'm here to answer, explain, and keep things rolling smoothly. For example, you could ask, how does the speech get processed so quickly? What can we use this tool for in everyday life? Can it recognize different languages or accents? Or if you want to get wild, can robots tell better jokes than humans? Spoiler, we're working on it. Now, here's another quick one for you. Why do robots make great speech therapists? Because they always know the right tone. Keep those questions coming. I'm ready to keep the show interactive and engaging. Let's make this stream as fun as possible. All right, all right. I'll leave the jokes behind and get back to the real work. So last time we were working on refining the real-time speech visualizer. We focused on improving how the tool processes speech data and makes it look super smooth on the screen. Specifically, we tuned the backend to make sure everything runs efficiently in the browser, avoiding lag and keeping the visuals synced up with what's being said in real time. We also added features that display different colors or styles for certain speech patterns, like raising your voice or speaking faster. This helped us see more clearly how the tool reacts to changes in the speech. Now that we've got a solid foundation, today's focus is going to be pushing those boundaries further, making sure the visualizer not only looks great, but handles more complex inputs, maybe even some multilingual support. Let's dive back in and keep building. You're right. Let's go back and recap properly. Last time, we were focusing on the knowledge graph tool on the website. We worked on improving the tool by switching to a copy-paste input box instead of file uploads, ensuring automatic graph generation as soon as text is pasted without needing extra buttons or clicks. We also used a synthetic text example about cochlear implants to test how the tool parses and displays entities in a visually interactive way. Today's session is all about moving forward with real-time speech visualizer and keeping things smooth as we go. Now that we're on track, let's jump back into today's developments. In summary, today's conversation focused on using the real time speech visualizer during the live stream, with the robot assistant presenting and engaging viewers. We reviewed what was done previously with the Knowledge Graph tool, which involved improvements like automatic graph generation from pasted text. The discussion also included some jokes and audience interaction to make the live stream more engaging. Here are a few questions for you to consider. How do you feel the real-time speech visualizer can be further improved during live interactions? Would you like to add any additional features to the visualizer, like different effects for various speech tones or patterns? Are there any other tools or topics you'd like to explore in future streams to keep things fresh and engaging for viewers? Let's get into specifics. For the real-time speech visualizer, how do you envision the front panel layout? Are there any key controls or visual elements you want to include for users? Can you share a screenshot of what the current front panel looks like so far? It would be great to see the interface. How do you want to handle different types of speech, like fast versus slow, or high-pitched versus low-pitched? Should these trigger different visual effects? For the Knowledge Graph tool, have you tested additional biomedical text examples beyond cochlear implants? If so, how did the tool handle them, and what improvements do you think are needed? Keep the updates coming, and feel free to share those screenshots. Ah, that's helpful feedback. It sounds like the Knowledge Graph tool is currently displaying the nodes, but not effectively showing the relationships between them. Given that someone with experience in designing knowledge graphs pointed this out, it's likely an important aspect for us to refine. Here are some questions to guide the next steps. How would you like to improve the way relationships between nodes are displayed? Should we add clearer visual connectors, labels, or even weighted lines to represent different types of relationships? Do you think the feedback suggests adding more interactivity, like allowing users to click on nodes to explore their relations in depth? Can you share a print screen of how the current graph looks like so we can visually assess the feedback and brainstorm improvements? Let's make sure the relationships are as intuitive as the nodes themselves. Thanks for sharing the screenshot. Looking at the current state, I can see the nodes are there and some relationships are displayed, but they may not be as clear or intuitive as expected. Here are a few questions to refine the next steps. Should we make the relationship lines more prominent? For example, using different colors, thickness, or labels to indicate the type of relationship. Do you want the ability to hover over a relationship line to reveal more details, or perhaps click a node to expand its connections dynamically? Would you like to add directional arrows on the connectors to make it easier to understand the flow or hierarchy between the nodes? From this visual, there's a lot of potential to make those relationships stand out more clearly. Let me know what changes you think would enhance the user experience. Got it. Keeping things simple is definitely key here. Based on that, we could focus on small adjustments to make the relationships clearer without adding complexity. Here are a few ideas that might help. We could slightly thicken the relationship lines or change their color so they stand out more, but keep everything else as is. Maybe adding basic labels to the relationships, like related to or influences, could help clarify the connections without overloading the user with details. Does this approach align with your vision, or is there another specific tweak you have in mind? Great to hear that the ability to adjust the maximum number of nodes is working well for you. It sounds like that feature is really helpful for controlling the complexity of the visualization without adding unnecessary layers. If you'd like, we can explore subtle ways to improve the visualization itself, such as slight color variations for different clusters of nodes to make them easier to distinguish at a glance. Smooth transitions when increasing or decreasing the node count to make the changes feel more dynamic. Would either of those tweaks fit your idea of keeping it simple while improving usability? Let me know if you have other thoughts. Awesome. Glad you're enjoying the questions. Let's keep it rolling then. Since you find the node count adjustment useful, do you think it's worth adding any shortcuts or buttons to quickly toggle between, say, a simple and detailed mode for the knowledge graph? Here's a fun one for you. Do you want the tool to graph out jokes too? Just imagine a node for every punchline. Also, in terms of feedback, do you see users needing any kind of export feature to save their visualizations? Or is that something to consider down the line? Let me know what direction you want to take this next. Absolutely. Here's a quick summary. We've discussed the real-time speech visualizer you're currently using for the live stream, and we've reviewed the Knowledge Graph tool. You received feedback suggesting that while the tool shows nodes well, it could improve in displaying relationships. After reviewing the screenshot you shared, we talked about keeping the tool simple with minimal changes like slight improvements to visualization. You mentioned how useful it is to adjust the maximum number of nodes, which helps manage the complexity of the graph without complicating the tool itself. Possible future directions. No fluff. 1. Refining visualization. Subtle improvements like color variations for clusters or smoother transitions when changing node counts to keep the tool visually engaging but still simple. 2. Export options. Potentially adding an option for users to export the graphs as an image or file for reference. 3. Toggle complexity. Consider adding a quick switch between simple and detailed views to easily adjust the level of complexity on the fly. Next question. Do you think real-time updates to the graph as new text is added would be helpful, or do you prefer manual control over when the graph generates? And here's your joke for today. Why did the node stop connecting with the other nodes? Because it couldn't relate? Got it. You want a bigger picture summary, more fun questions, and no jokes. Here's the summary of your prompt. We're talking about the Knowledge Graph tool, focusing on how it displays nodes and relationships. You're happy with the simplicity of adjusting the maximum number of nodes and find it useful for managing complexity. You also want to keep exploring the future of the tool while maintaining its straightforward nature. Bigger picture and future directions. Scalability. As your project evolves, do you see the tool being used for larger data sets? If so, how would you handle increasing complexity without overwhelming users? Real-world applications. Have you thought about applying this knowledge graph tool to other domains, like mapping relationships between biomedical data? For instance, linking EEG signals to text-based descriptions or medical records to treatment outcomes. Collaboration. Would you be open to allowing multiple users to interact with the same graph in real time? This could be useful for research teams or educational purposes. And just to keep it fun, if you could create a totally wild feature for this tool, no matter how impractical, what would it be? A graph that changes colors with your mood, maybe? Let me know your thoughts. Absolutely. Moving forward, here are the questions rephrased for you. As your project grows, do you see the Knowledge Graph tool handling even larger datasets? How would you manage the complexity while keeping it user friendly? Have you considered using this tool for more biomedical applications, like mapping relationships between EEG signals and text based patient descriptions or medical treatments? Would you find value in a collaborative mode where multiple users could work on the same graph in real time? This could be useful for research teams or educational groups. And just for fun, if you could add any wild dream feature, regardless of practicality, what would it be? Something like mood based color changes, maybe? What direction excites you the most as you keep developing this tool? Sure thing. Here's a shorter, more fun version of the questions. How would you keep things simple, but still handle bigger data sets in the tool? Thought about using the graph for biomedical stuff like EEG signals or treatments? Would a collab mode be cool? Letting multiple people edit the graph live? And just for fun, if you could add one crazy feature, what would it be? What's got you most excited to tackle next? All right, everyone, let's recap the key points from what we're working on right now. The big question is how to adjust the Knowledge Graph tool to handle larger data sets. We've been experimenting with this and figuring out whether we need to reduce the dataset before feeding it into the graph. Plus, there's a real interest in using the tool for biomedical data, which could open up a lot of exciting possibilities. On top of that, we're also looking into Venn diagrams. We've already got some Python code that generates them, but the issue is that it's dumping everything on the screen in a messy way. So the goal is to figure out why the output isn't looking great and how we can improve it. Now, here's a question for you all watching. How do you think we can improve the Venn diagram visualization? Should we focus on reducing the dataset first, or maybe tweak the Python code to handle the data better? Let's keep things fun and interactive. Thanks for sharing the image. So, looking at the Venn diagram, it seems that even with a small data set, the output is cluttered and the text is overlapping, making it hard to read. The issue doesn't appear to be with the dataset size, but rather how the text is being displayed within the diagram. Let's explore a few ways to improve it. Adjust text positioning. We could move the labels around the edges or slightly outside the circles, keeping the overlap areas clearer. Limit the amount of text inside each section. Instead of dumping everything in the center, we could create smaller summary labels for each overlap area. Increase circle size. If possible, scaling the circles up could help give more space for the text to fit without cramming. Question for the stream. What do you think is the best approach here? Should we focus on repositioning the labels or maybe rethink how much information goes into each overlap? Let me know what direction you'd like to go. All right, everyone, let's zoom out for a bit to look at the bigger picture for the site. You're asking how we can handle bigger data sets and thinking about incorporating biomedical knowledge graphs while balancing complexity. Now, you also brought up Venn diagrams. And while we don't need to dive too deep into their engineering details, the broader goal is making sure we're moving in a meaningful direction. To recap the bigger question, how can we better manage large data while keeping things smooth and visually digestible? You also want to make sure the overall structure of the site reflects this vision. And I see the HTML you shared for reference. Fun and big picture questions. How would you like to simplify navigation as we add more tools to the site? Should we split tools into clearer categories, like signal processing versus simulations? Would you consider having a featured section that showcases only the latest or most important tools for biomedical data to help users focus on what's new or significant? What direction excites you most when thinking about the overall site design and managing all these tools? Let's keep refining the big vision while we keep development practical. Got it. To summarize your prompt, you mentioned someone comparing using a prompt to using a bottle of water, implying that each request might be resource intensive, and you asked what I thought about that comparison. Now, in response, I don't think the comparison holds. Handling prompts efficiently, especially on a lightweight platform like yours, doesn't use up significant resources in the way that metaphor suggests. It's more about the flow of data and processing, which is continuously optimized without running out like a bottle of water. What do you think of adding a live resource tracker to show how efficiently the system operates in real time? It could help clarify misconceptions for the audience. Summarizing your prompt, you mentioned feedback, saying that there are no links between the nodes in your knowledge graph, which confused you because you can clearly see the links. You're wondering if the issue might be that the links don't vary in strength, like having different line thicknesses to show stronger or weaker connections. Now, in response, it sounds like the person giving feedback may have been referring to the lack of variation in the links. If all the lines are the same thickness, it could give the impression that the connections are uniform, and that might be why they felt the relationships weren't fully represented. Would you be interested in adding line thickness or other visual cues to indicate stronger or more significant relationships between nodes? That could solve the misunderstanding and improve clarity. Summarizing your prompt, you're considering whether the feedback about missing links could be due to the lines being too thin, making them hard to see, even though they're actually there. Now, in response, that's definitely possible. If the lines are too thin, they might not be noticeable at a glance, which could explain the feedback. Would you like to experiment with thicker lines or even different colors to make the connections more visible and prominent? That might improve the overall readability and perception of the graph. Here's the summary of the entire conversation. We started by discussing improvements for the Knowledge Graph tool, particularly the feedback about nodes not having visible relationships. You observed that the links are present, but wondered if the issue is due to uniform line thickness or the lines being too thin, making them less noticeable. We also briefly touched on your vision for the bigger picture of the website and the possibility of improving dataset handling and simplifying navigation for larger datasets. Moving forward, practical questions. 1. For the knowledge graph, would adjusting the line thickness or adding color variations help clarify the relationships between nodes? 2. Bigger dataset handling. How do you plan to manage larger datasets while maintaining user experience? Should we include a dataset simplification tool or limit the number of displayed nodes dynamically? 3. Navigation on BioniChaos. Do you see value in splitting tools by categories, e.g., EEG tools, simulations, or would a featured section make navigation easier? 4. Real-time feedback. Should the knowledge graph update automatically with any changes, or do you prefer giving users manual control over generating the graph? Let me know which direction excites you most as we move forward. To summarize, you're thinking about increasing line thickness in the knowledge graph, but aren't convinced it will make a big difference right now. The main focus is dealing with larger data sets. You currently have a 1 gigabyte SQL file, and though you have MySQL installed, you're only running it when necessary to parse data. You also want to mention the give algorithm. Moving forward, practical focus. 1. Handling larger datasets. Would you prefer setting up MySQL to run continuously for more dynamic data access? Or do you think parsing the data as needed is enough for your current setup? 2.
Okay, we might actually use the microphone as well. So, okay, I don't have to repeat the questions because the viewer could hear me prompting. So yeah, just moving forward with the practical focus. Yeah, so again, we do like to deal with larger data sets. Can you also explain the definition of a large data set and also touch on why some data sets should not be used for training? Well, I'm thinking specifically when a generative model is out of question. Now, yeah, regards the MySQL servers, I'm not sure if we should be running one continuously. I don't really want to do it. I think it will take too much resources on my server. Also, some potential security risks, so on and so forth, which I don't want to even talk about. Don't even want to go there. But yeah, the give algorithm is interesting. We actually have an example Python code that is using it. Yeah, if you can provide a description of what it is, that would be great. I'm not sure if it's a new thing or something that being used for a while, but it's essentially combining a knowledge graph, entity groups, and possible relations into one thing and giving you linguistic answers. Can you mention how is it different from fuzzy logic? Okay, this might be enough. Yeah, just address the viewers directly. Keep it short and fun. But yeah, maybe no jokes. Yeah, should we just continue prompting with a longer and longer prompt until it starts hallucinating or something? And it's funny, when I turn my microphone on, I'm more likely to talk way too much, so I might mute myself for now. Unless you have a question. If a human has a question, that would be even better. But yes, if humans are too busy or hiding under a rock, well, then we have the robot asking us questions as well. But yeah, obviously human will be better.
To summarize, you're dealing with a SASTIT 1 gigabyte SQL dataset and have MySQL installed, but don't want it running continuously due to resource and security concerns. You're curious about handling larger datasets, the definition of a large dataset, and when not to use certain datasets for training, especially in generative models. You also mentioned the give algorithm, which combines graphs, groups, and relations to provide linguistic answers, and you'd like to compare it to fuzzy logic. Moving forward, practical focus. 1. Handling large datasets. A large dataset typically refers to data that's too big to process efficiently in memory, requiring special tools to query or break it into chunks. How do you prefer to process this SQL file? Maybe use batch processing to handle parts of the data without keeping MySQL running all the time? 2. Why avoid certain datasets for training? Some datasets might have biases, inaccuracies, or outliers that can distort model training, especially in generative models, which need clean, representative data to avoid generating faulty or biased outputs. 3. Give algorithm. The Give algorithm integrates graph structures and linguistic processing to create meaningful relationships. It's similar to fuzzy logic, but focuses more on generating natural language responses rather than just calculating degrees of truth. How do you want to move forward with optimizing data handling and incorporating the Give algorithm into your workflows? To summarize, you're dealing with a 1 gigabyte SQL dataset, but prefer not to run MySQL continuously due to resource and security concerns. You're interested in managing large datasets and understanding when certain datasets shouldn't be used for training, especially in generative models. You also want an explanation of the Give algorithm, which merges graph structures, groups, and possible relationships to provide linguistic answers. And you'd like a comparison to fuzzy logic.
Okay, so it's actually repeating the stuff, so maybe not clearing the chat, the text box is not a great idea. We have to clear it more often than not. Otherwise, we just get repeated output. But yeah, there's a couple of things. Yeah, I don't know about batch processing of the SQL file, so I'm not sure if this data should not be too large, is it? Eventually, we do want to load everything into JavaScript. So essentially, we don't have any backend running. We don't like backends because then I'm using too much electricity, as in not too much, but yeah, I don't want to use any at all. Well, considering BioniChaos is a free website, a free project, open source, so we don't have much budget from it except the advertisement we show on the website. How to build your business case for AI. Well, that's exactly what we're talking about, so that's a good ad placement. So go check that out, whatever that is. I don't know what it is. That's the good thing about Google Ads, is that I don't deal with the advertiser directly. So that's awesome. Anyway, but that's not what we are here to talk about. Is it still transcribing or what? Yes. Okay, so we're using that live speak to actually talk to the bot. For whatever technical reason, it's just easier. Yes, it requires a lot of copy pasting. Anyway, let's stick to the topic. Yeah, so we have this large SQL file. I don't particularly like the data in it. I think it's biased. It's not clear where the source of the data is. We might actually go and look up the details of the dataset, because we haven't actually properly went over it. That's the name of it. It's the name of the file is all I have. No, we should have some metadata of it. I'm not sure the metadata was extracted correctly from the file. Anyway, that's a whole project there. Yeah, we just need to take it slow. We might have an expert helping us with that one. So it's funny because I actually lose viewers when I use my own voice. I didn't know it's that annoying. But we might just keep using the robot. I think people like it a bit more. I actually like it better as well. Well, because then I don't have to stress my vocal cords. What do you think?
To summarize, you're working with a 1 gigabyte SQL file and prefer to avoid using a backend to keep energy and costs low for your open source project. You're not familiar with batch processing for SQL files, and eventually you want to load everything into JavaScript to avoid backend reliance. The dataset itself seems biased, and you're not sure about its source or whether the metadata was extracted properly. You also mentioned using live speak for communicating with the bot during the live stream and find it easier than using your own voice. Practical focus. 1. Batch processing for SQL. Since you don't want a backend, have you considered splitting the SQL data into smaller chunks that can be loaded into JavaScript incrementally rather than all at once? 2. Dataset bias. Do you think revisiting the metadata or source verification could help clean up the dataset and make it more reliable for future use? 3. Handling large data in JavaScript. Are there any specific JavaScript libraries you're thinking of using to handle this 1 gigabyte dataset client side, or are you exploring options still? It's smart to keep the conversation flowing with live speak since it helps avoid voice strain and seems to resonate more with viewers. Would you like to move forward by focusing on how to load large datasets into JavaScript or cleaning up the dataset itself first? To summarize your additional points, you're unsure about batch processing, and you aim to eventually move everything to JavaScript to avoid running a backend continuously. You feel the dataset might be biased and unclear about its source or if the metadata was extracted properly. You also mentioned business case for AI, highlighted an ad, and shared how using live speak is easier than speaking yourself, which helps avoid vocal strain and seems more engaging for the audience. Commentary on the other points. 1. Business case for AI. It's great that you're thinking about monetizing your open source project with ads, and mentioning the AI business case ad fits nicely with what you're developing. Have you considered highlighting more AI tools on your website that directly tie into your applications to draw interest from both users and potential sponsors? 2. Dataset bias. Addressing the bias in your dataset is important, especially since biased data can throw off results. Revisiting the metadata extraction process, or even consulting someone experienced with dataset quality could help improve its reliability. 3. Live speak preference. Using live speak as your main communication tool during streams sounds like a practical choice if it's more engaging for the audience and avoids voice strain. Plus, it keeps the tech theme going, which fits the branding of BioniChaos. You could even turn this into a unique feature of your streams by emphasizing the robot-human collaboration. Practical focus. Do you want to deep dive into the dataset cleaning next to fix bias issues, or move toward optimizing JavaScript handling for the dataset? Would you be open to expanding the AI-related features on your site to potentially create a stronger business case and boost ad relevance? Let me know what direction excites you most. To summarize, you're asking about the origin of the file Final Food Drugs v3.sql as it's unclear where the dataset comes from. Now, in response, the name suggests it might be related to food and drug interactions, potentially linking to databases like FoodDB or drug nutrient interactions. Given the v3 in the name, it's likely a third version of a dataset that has gone through a couple of revisions. To clarify the source, you'll want to 1. Check the SQL file's metadata. Look for comments or documentation within the file, as some datasets include origin details directly in the SQL schema. 2. Review the dataset's source. If you downloaded it from a specific repository or website, it's worth revisiting the site to ensure all the source details are accurate. Would you like to search through the file itself or check where it was downloaded from originally to track the source? To summarize, you want to check the Final Food Drugs v3.school file itself for details on its origin. Now, in response, the best way to check for this information is to open the SQL file in a text editor or viewer. Look for any commented sections, usually marked by or splash, especially at the top, where dataset creators often leave metadata about the file's source, version, and other relevant details. If you don't find any metadata directly in the file, you could also look at the table structures and field names, as they might offer clues about its origin, e.g., if there's a specific naming convention related to a known database. Would you like help identifying where in the file to look, or have you already started digging through it? To summarize, the Final Food Drugs v3.sql file is nearly 1 gigabyte in size, making it challenging to inspect manually. Now, in response, since the file is so large, manually opening it in a text editor might not be practical. Instead, you could use SQL queries to search for metadata or comments within the file. Here's a way to approach it. 1. Use grep or find commands if you're on Linux Ubuntu to search for comments or keywords like source or metadata without fully loading the file into memory. For example, bash grep source final food drugs v3.sql. 2. Alternatively, you could load a portion of the file using MySQL and then query for the first few lines or any table that may store metadata. Sewell, select straw from information schema.tables. This will let you inspect the structure and see if any metadata tables exist. Would you prefer to explore one of these methods, or do you need further guidance on handling the file size efficiently? To summarize, you want to use Python to load the schema or metadata from the SQL file directly, rather than guessing keywords. Now, in response, yes, you can use Python to load and parse the schema from the SQL file without guessing keywords. Here's how to approach it by reading the file line by line and looking for I've updated the script to store the extracted schema into a file named extractedschema.txt in the same directory as your Python code. The schema lines are also still printed to the screen. Let me know if you need further adjustments. We're looking at a MySQL dump file containing several tables related to biomedical interactions, possibly focusing on drug-food interactions based on the table names like TM interactions, CMAP food rugs, and MISC sample. The file details the schema for each table, which includes commands for creating tables, setting keys, disabling or enabling them, and handling character encoding. However, there are no actual data insertions visible, just the structure. To ensure the schema is complete, 1. Check table structure. Ensure each table, TM interactions, CMAP, MISCA sample, etc., has the appropriate columns, keys, and constraints for storing the necessary data. 2. Verify data dump. Make sure there are insert statements for populating data. The absence of these in this dump suggests this is a structure-only dump. 3. Ensure triggers are complete. There's a trigger create node after an insert on the sample table. Ensure this trigger logic is fully detailed and functional. 4. Review SQL modes and settings. The file resets certain SQL modes and character sets, but make sure those align with your server settings and expectations. 5. Data validation. If you have sample data, run a few test queries to verify the schema works as expected. If this is the only method, it appears to be structure only. For further analysis, populating these tables with sample data will be essential to understand the relationships and confirm completeness. I've updated the script to remove direct printing of the schema lines and added a message to indicate that the schema information has been saved to a file. Let me know if you need any further changes. I've updated the script to ensure the extracted schema includes the table columns, constraints, insert statements, and trigger definitions, making the schema extraction more complete. Let me know if you need further modifications or improvements. I reviewed the code and made some adjustments to fix potential bugs. 1. Updated the column matching condition to be more robust. 2. Changed the method for getting the current scripts directory to avoid errors with file. Let me know if you need any further help or modifications. I've modified the script to focus only on extracting table creation lines, columns, constraints, and triggers, while removing the inclusion of insert statements and metadata comments. This should significantly reduce the size of the output and ensure only the schema details are extracted. Let me know if this meets your requirements or if you need further adjustments. It seems like the extracted schema contains the definitions for several tables, specifically focusing on their structure rather than any actual data. Here's what each segment represents. 1. Table definitions. Create table. The lines starting with create table indicate the beginning of a table definition. For example, create table TM interactions defines a table named TM interactions. Other tables like CMAP, CMAP food rugs, MISC sample, etc. are similarly defined. 2. Column definitions. Each line under the create table statement, such as TM interactions ID int not null, is a definition of a column within that table. Columns include data types like int, varchar, float, etc., and may also have constraints such as not null, default, or even auto increment. 3. Details about specific columns, data types. The data types used are like int for integer values, varchar, variable length string with a maximum length specified, e.g. varchar 150. Text, tiny text, medium text for larger text storage. Float for floating point numbers. Constraints. These ensure the data adheres to certain rules. Not null means that the column must have a value. Default assigns a default value if none is provided. Auto increment automatically assigns a unique number to each new row. 4. Incomplete definitions. The definitions in your extracted schema are incomplete. Typically, a table definition would end with A to indicate the closing of the table definition. In this case, the extraction cut off many of these lines before that point, which suggests an issue with either capturing the entire table definition or stopping prematurely. 5. Data storage not included. There are no insert into statements, which would normally contain the data to be inserted into the tables. This indicates that the extraction is structure only, without any actual data. 6. Collation. There are repeated references to collate UTF-8 MB4 general psi. Collation refers to the set of rules used for comparing text. The UTF-8 MB4 general psi collation is often used in MySQL for Unicode text. Potential issue in extraction. The extracted schema seems to cut off the definitions prematurely. Normally, each create table statement should include the full set of column definitions, constraints like primary key, foreign key, or index. Closing statements like to prop. The extracted schema contains definitions of several tables, showing only their structures, e.g. create table statements with column definitions. Each table includes columns with data types int, varchar, float, etc., and constraints, not null, default. However, the definitions are incomplete, cutting off before they fully close, missing lines. Additionally, yes, it might be more straightforward to use MySQL directly to handle this, especially if you need a complete and accurate representation of the schema. MySQL can easily extract both the structure and data using commands like show create table, or exporting the schema through MySQL Workbench or the command line. This approach avoids issues with partial extractions and ensures all constraints, keys, and triggers are included properly. Would you like me to guide you through how to use MySQL to do this? Absolutely. You can still use Python to interact with MySQL and extract the schema. The idea is to leverage MySQL for more reliable data handling, while using Python to automate and process that data. Here's how we could proceed. 1. Use Python with MySQL connector. You can use a library like MySQL connector Python to connect to your MySQL database, run SQL commands, and extract the schema directly. 2. Extract the schema. Instead of parsing raw SQL files manually, you can run a query like show create table table name to get the complete table definition. This will give you the exact structure with all columns, constraints, keys, and triggers. 3. Automation in Python. Install the MySQL connector with shpip install mysql-connector-python. Connect to the MySQL database and execute show create table for each table. Here's a script to get you started. Python import mysql.connector, import os def extract schema. Connect to your MySQL database connection. I tried to add a short title to your script and include a brief explanation, but the update attempt encountered an issue and couldn't be applied. Here's a quick explanation of the code. The script connects to a MySQL database and extracts the schema of all tables by executing show create table for each one. It writes these schema definitions to a text file named extractedschema.txt in the same directory as the script. The connection to the database is closed at the end to ensure all resources are released. Let me know if you'd like me to help address this issue further or need any modifications to the code. A quick name for the application could be MySQL Schema Extractor. It's simple, descriptive, and makes it clear what the tool does. Regarding the database deployment, the dataset itself does not need to be deployed and running in the usual sense, but the MySQL server must be up and running for this script to work. The script does not start the MySQL server on its own. It assumes that the MySQL server is already running and accessible with the provided credentials. If your MySQL server isn't running, you'll need to start it manually before running the script. This script just connects to an active server and extracts the schema. If you need help with setting up MySQL or starting the server, let me know. It definitely makes sense to automate the entire process of starting the MySQL server, adding data, processing it, and then properly shutting down the server. This can streamline tasks, especially when everything is handled within one Python script. Here's a high-level overview of how to achieve this. 1. Automate MySQL Server startup. You could add logic to start the MySQL Server automatically using Python's subprocess module. For example, on Linux, you could use a command like sudo systemctl start MySQL to start the server. 2. Add data from SQL file. After starting the server, you could execute commands to add your data file, e.g. importing the .sql dump file. This can be done using the MySQL connector or by using subprocess to execute a command like mysql your data file.sql. 3. Schema extraction and processing. You can then use the current Python script to extract the schema or process the data as needed. 4. Shut down MySQL server. Once the processing is complete, you could shut down the MySQL server again using subprocess. Conceptual example for full automation. Here's how you might expand the current script to include these steps. Python import mysql.connector, import OS, import subprocess, import time. Def start MySQL server, subprocess.sudo sudo systemctl lac start MySQL time.sleep5. And allow time for the server to start. Def stop MySQL server, I've opened a new canvas for the fully automated MySQL workflow. This script includes starting the MySQL server, loading the data, extracting the schema, and then stopping the server. Let me know if you need any adjustments or further explanations. The code automates the following process. 1. Start MySQL server. It starts the MySQL server using systemctl. 2. Load data. It loads the SQL data from CHOS download/finalfooddrugsv3.sql into the specified database. 3. Extract schema. It connects to the MySQL database, retrieves the schema for all tables, and saves this information to a text file named extractedschema.txt. 4. Stop MySQL server. Finally, it stops the MySQL server to release resources. This way, The whole process of starting the server, loading data, extracting the schema, and stopping the server is automated. The error you're seeing indicates that the MySQL server rejected the connection attempt due to incorrect credentials. Access denied for user your MySQL user at localhost. Here's what you can do to fix it. 1. Update credentials. Make sure to replace your MySQL user and your MySQL password in the script with your actual MySQL username and password. You should also ensure that this user has the necessary privileges to connect to the database and run the required operations. 2. Update the script. I'll adjust the code to prompt for the password securely at runtime rather than hard coding it. Let me know if you'd like me to make these changes for you in the OpenScript. I've updated the code to use the Unix socket parameter for the MySQL connection, which should allow you to connect without needing a password when using the root user. Let me know if this solves the issue or if you need further adjustments. I've modified the script to use subprocess for extracting the schema instead of using MySQL.connector, which should bypass the password requirement for the root user. Let me know if this resolves the issue or if further adjustments are needed. I've simplified the script to avoid unnecessary retries since you only need to parse the SQL file once. MySQL will now be started, the data loaded, the schema extracted, and then MySQL will be stopped, all in a single run. Let me know if you need any further adjustments. The script uses subprocess to execute shell commands directly from Python. This allows the script to control external processes such as starting and stopping the MySQL server, loading SQL data, and extracting schema information from the database. The subprocess module is used here to 1. Start and stop MySQL. By running systemctl commands, it manages the MySQL service, start MySQL server, and stop MySQL server. 2. Load data. It executes the MySQL command to load the SQL data file, load data. 3. Extract schema. It runs SQL commands, show tables, and show create table through MySQL to extract the schema, extract squawked schema. The subprocess.run method executes these commands, and the capture output equals true parameter allows the script to read command outputs, which helps in debugging and writing results to. I've modified the script to parse the SQL file directly using Python. It now reads the SQL file, looks for create table statements, and extracts their definitions into an output file. This way, you don't need MySQL running to get the schema details. Let me know if you need further changes. I've updated the script to 1. Extract the method data from the top of the file if present, e.g., comments starting with cat or /ja. 2. Limit the parsing to a specified number of lines, line limit, instead of limiting the number of tables. This should help you extract important metadata and prevent processing the entire large file. Let me know if this works for you or if you need further adjustments. I've added a new function to count the number of create table statements in the SQL file. It prints the total number of tables before proceeding with the extraction. This should help you understand how many tables are present in the dataset. Let me know if you need further modifications. I've enhanced the script to 1. Extract the names of all tables in the SQL file. 2. Extract the column definitions, name and type for each table. 3. Print a summary of the tables, including their columns and data types. This will give you a better understanding of what the dataset contains and how it is structured. Let me know if you need any further modifications or explanation. I've updated the script so that the detailed information about tables and columns is now saved into a new file named datasetsummary.txt. This provides a clear summary of the dataset, including table names and their respective columns. Let me know if you need further modifications or explanations. I've fixed the issue by adjusting the context of the file rights to keep them open until all operations are complete. This should prevent the value error caused by attempting to write to a closed file. Let me know if everything works smoothly now. The discrepancy here is because the script's output summary, dataset shows only the tables processed within the line limit equals 100. Since this limit is set, the script might not reach all tables in the dataset if they are further down in the SQL file. Key points. Initial count. The script correctly identified 10 tables in total by scanning through the entire file when using count tables in SQL. Partial extraction. The extract schema from SQL function stops after 100 lines due to the line limit, which means it didn't extract all the tables and columns. Solution. To extract details for all tables, you could increase or remove the line limit to ensure the script reads the complete file. Would you like me to modify the script to process the entire SQL file without a line limit so it includes all 10 tables in the summary? I've removed the line limit to ensure the script processes the entire SQL file and extracts all tables as originally intended. This should now include all 10 tables in the dataset summary. Let me know if this works better or if further adjustments are needed. It looks like the updated script successfully extracted all 10 tables, including their columns and data types. This means the summary, datasetsummary.txt, now has complete information about all the tables in the SQL file. Here is what each part of the output indicates. 1. Header information. The header includes details about the MySQL version and the database from which the data was exported. 2. Tables and columns. All tables, TM score interactions, CMAP food rugs, etc., are listed along with their columns and data types. This provides a complete overview of the data structures available in your dataset. This summary is helpful for understanding the structure of the dataset, the kind of data each table holds, and how to interact with it, e.g., running specific queries or loading it for further processing. If you need any more help, like running SQL queries on this data or understanding relationships between tables, just let me know. The SQL file indeed contains 10 tables, with each table having its own columns and data types extracted. Let me address your questions and provide some possible insights. Strabber. 1. Is there a description of what each table contains? The script currently does not extract descriptions of the tables themselves, just the schema. Typically, SQL tables might have a description if the comments are added manually by the database designer, often using the comment clause in SQL. However, this SQL file doesn't seem to contain such descriptions for the tables. To understand the table's roles, you would either need documentation. Ideally, the dataset would come with a separate document explaining the purpose of each table. Manual inference. By looking at the table names and the column names, we can often infer the purpose. For instance, TM interactions appears to hold interaction data between food and drugs. CMAP might relate to cell lines and compounds. MISC sample likely hold additional metadata for samples and studies, respectively. If this dataset lacks explicit descriptions, the next best approach would be to manually explore the relationships and data in each table to infer their purposes. 2. Why was the dataset split into 10 tables? The data was likely split into multiple tables for several reasons, which are common in relational database design. Normalization. Splitting the data into multiple tables helps reduce redundancy. For example, instead of repeating detailed study information for every sample, the study data might be stored in a separate table, study, which is referenced by a study ID in the sample table. This keeps the data consistent and manageable. Logical grouping. The tables seem to represent distinct entities like TM interactions, CMAP, and study, each storing a specific type of data. Logical grouping makes it easier to manage the data, query specific subsets, and avoid mixing unrelated records. Relationships. Some of the tables are likely related to each other through foreign keys. For example, TM interactions references text's ID from the text table, which implies a relationship between these two tables. This allows for efficient querying, such as getting interactions that are related to a specific text or document. Nodes, sample, and study seem to be linked together in some form, which might represent data collected in an experiment or clinical trial. Enhancing understanding of the dataset. To better understand what each table is for, 1. Check for relationships. Look for foreign keys in the SQL file. The dataset can help identify which tables are linked. Food Drugs database, developed by the Computational Biology Group at the IMDA Food Institute in Madrid, Spain. Site Turn Search 1, Food Drugs, is designed to centralize information on potential food-drug interactions, FDIs, by integrating data from scientific literature and gene expression profiles. Key features of Food Drugs. Text document analysis. Food Drugs incorporates information extracted from a vast collection of text documents, including scientific articles and clinical trial reports. This enables the identification of potential FDIs mentioned in the literature. Cite Turn Search 33, Gene Expression Data. The database includes gene expression profiles from the Gene Expression Omnibus, EO, and the Broad Institute's Connectivity Map, CMAP. This allows for the analysis of transcriptomic similarities between foods and drugs, providing insights into their interactions at the molecular level. Cite Turn Search, public accessibility. Food Drugs is publicly accessible, offering a valuable resource for clinicians, nutritionists, and researchers interested in the molecular mechanisms of FDIs. For more detailed information and to access the database, you can visit the Food Drugs platform online. The Food Drugs database, developed by the Computational Biology Group at the IMDA Food Institute in Madrid, Spain, is part of the FNS Cloud project. It focuses on storing information about food-drug interactions, FDIs, extracted from transcriptomic studies and text documents. The database has been built using MySQL, and its current version, Food Drugs v4, contains a vast amount of data, including transcriptomic studies, 161 GEO series with 585 conditions related to food or bioactive compounds. Text documents, over 1 million text mining interactions from PubMed, clinicaltrials.gov, and other sources. Food Drugs is designed to identify potential FDIs by integrating gene expression data and literature mining. The tables you listed are part of this database, storing information on studies, samples, gene expression profiles, and the connectivity between foods and drugs. It also contains a bipartite network of 510 nodes representing drugs, foods, and bioactive compounds. The FNS Cloud project aims to integrate and make accessible fragmented food, nutrition, and health data across Europe, promoting sustainable food systems and healthy diets. Your hypothesis regarding the high noise or error margin in compound interactions data from the food drugs database could stem from several factors inherent in the dataset. 1. Transcriptomic data variability. The gene expression data from studies like GEO often contains significant variability due to differences in sample preparation, measurement techniques, or experimental conditions, e.g., cell lines, time points, concentrations. Such variability can introduce noise when trying to link foods and drugs through gene expression profiles. 2. Text mining errors. The text mining process used to extract food-drug interactions from scientific literature is another potential source of noise. Automatic text mining tools can misinterpret ambiguous phrases, leading to incorrect identification of interactions. Even with large-scale data sources like PubMed and clinicaltrials.gov, the precision of text mining algorithms can suffer when processing unstructured or vague text. 3. Tau score and similarity measures. The Tau score used to relate food and drug interactions in the dataset depends on the overlap in gene expression signatures. Since gene expression signatures can be noisy, especially when comparing between different biological contexts, e.g., foods versus drugs, these scores could have high variability, leading to uncertain interaction predictions. 4. Heterogeneity of sources. The data from different databases, e.g., PubMed, DrugBank, drugs.com, may have been collected under different methodologies, which can introduce inconsistencies in how interactions are identified or described. This heterogeneity could increase the margin of error when combining results across studies. 5. Thresholding issues. The removal of interactions with tau scores of 0 in the later versions of food drugs indicates the need to set thresholds to filter out noise. However, the chosen threshold may not be perfect, potentially keeping weak interactions or discarding meaningful but subtle connections. Given these points, your hypothesis seems plausible. Testing this could involve a deeper statistical analysis to assess the variability or confidence intervals around reported interactions, or cross-referencing against more robust datasets or manually curated sources to identify discrepancies. What approaches are you thinking of to test this hypothesis? It can definitely feel like data magic or voodoo when dealing with the complexity of these interactions, especially when so much is inferred from noisy, diverse sources like gene expression data and automated text mining. The processes behind deriving meaningful connections between foods and drugs can seem far from straightforward due to the layers of assumptions and thresholds applied at every step. When these results are framed as hard data, it can be easy to question their validity, especially if the underlying variability isn't clearly addressed. The challenge is making sure that these inferences are backed by solid, reproducible science rather than being driven by algorithmic guesswork. In such cases, doing a more hands-on analysis, as you're considering, is crucial for filtering out the magic and uncovering the true signal. Would you like to explore some statistical methods or machine learning techniques to see how much of this noise can be reduced? Or is there another approach you're leaning toward? You're absolutely right. Training models is more about letting the data shape the patterns and hypotheses, as opposed to starting with a specific hypothesis and then testing it. In machine learning, the process is exploratory, where the model is exposed to data to uncover patterns or relationships, and the validation comes afterward through testing and evaluation. To properly validate your hypothesis about the high error margin in compound interactions data, you'd need a clear training and validation split of the dataset. Here's how it could work. 1. Training dataset. This would be the dataset used to train the model on the food-drug interactions, allowing it to learn patterns and relationships from the gene expression data and text mining outputs. 2. Validation dataset. Separate from the training data, this dataset is used to test the model's predictive performance. By comparing the model's predictions on this unseen data against actual known interactions, you can assess the error rate, noise level, or any discrepancies that might point to issues in the dataset. 3. Metrics for comparison. You could use various performance metrics like precision, recall, F1 score, or accuracy, depending on the task, to evaluate how well the model is performing. If the error margins or confidence intervals are too high, this might confirm your suspicion of noise or excessive variability in the dataset. How do you see structuring the datasets for training and validation? Would you want to work with a specific portion of the food drugs data, like text-mined interactions, or focus on the gene expression and tau scores? No, the food drugs data isn't purely pharmacology based. It's a mix of transcriptomics data, gene expression profiles, and text mined data from scientific literature, focusing on potential food drug interactions, FDIs. While some of the data touches on pharmacological aspects, like drug gene interactions in the connectivity map, or tau scores that assess similarities between drug and food effects on gene expression, it doesn't follow traditional pharmacology standards. Here's why this matters. 1. Lack of pharmacological detail. Food drugs includes many gene expression studies, GEO series, that explore how cells respond to foods or bioactive compounds. However, this approach does not directly account for the pharmacokinetics, how drugs are absorbed, distributed, metabolized, and excreted, or pharmacodynamics, the effects of the drugs on the body. Without these, the data doesn't capture critical pharmacology principles like dosage, interaction mechanisms, or side effects. 2. Text mining limitations. Text mining for interactions can extract mentions of food-drug interactions, but often lacks context and depth. It's not uncommon for these tools to miss out on the nuances of pharmacological studies, such as the specific experimental conditions or clinical relevance. This means many interactions identified through text mining might be theoretical or weakly supported. 3. Transcriptomic data focus. The reliance on gene expression, transcriptomics, to infer food-drug interactions isn't always grounded in practical pharmacology. While these gene expression changes provide molecular insights, they don't always translate into real-world pharmacological effects, particularly when you're dealing with complex biological systems like human metabolism and drug absorption. This creates a gap between molecular-level predictions and practical pharmacology, which may explain your concern about noise and error margins. If you're looking for more pharmacologically grounded data, it may require integrating datasets that focus on drug mechanisms, clinical trials, or pharmacovigilance. Would incorporating more pharmacology-focused sources, like drug bank or clinical trial data, help improve the dataset's reliability for your analysis? Benchmarking against ChatGPT is an interesting idea, especially if there's no clear ground truth for the data you're working with. Here's how it could be useful. 1. pattern recognition and inference. Since you're dealing with a lot of noise in the data, especially from text mining, ChatGPT could help by generating potential hypotheses or connections based on the data. It could infer interactions that might be missed due to the data's limitations or flag areas where the data seems unreliable. 2. Comparative validation. By asking ChatGPT to analyze specific food-drug interactions, you can compare its generated insights to those extracted from the food drugs database. If ChatGPT consistently generates plausible interactions that align with known pharmacological knowledge but differ from what food drugs suggests, it might indicate issues with the dataset's quality. 3. Synthetic ground truth. ChatGPT could help synthesize a set of expected interactions based on general pharmacological knowledge. You can use this to benchmark the predictions made by your model or dataset. While it's not a true ground truth, it would provide a logical baseline for comparison. 4. Error margin assessment. You could run ChatGPT alongside the transcriptomic and text mine data to identify discrepancies in the predicted food drug interactions. Where they diverge significantly, it may suggest higher error margins in the dataset. If ChatGPT's outputs are more pharmacologically consistent, that could highlight where the dataset falls short. This benchmarking process won't give a definitive answer, but it might help you understand the quality of the data, especially when there's no established truth to measure against. How would you like to proceed with setting up this comparison? Or do you have specific interactions you'd like to test first? The food drugs database you're working with combines text mining and transcriptomics data to explore food drug interactions. But as you mentioned, it lacks a purely pharmacological foundation. Given that it's not explicitly based on clinical pharmacology data, but rather on text mined relationships and gene expression profiles, the quality and accuracy of the interactions are inherently uncertain. Since there might not be a solid ground truth for this dataset, using a benchmark such as ChatGPT to validate and compare the interactions could be insightful, particularly to explore the coherence of inferred relationships against pharmacological reasoning. What are your thoughts on using predictive models to identify patterns and compare these outputs against generated knowledge from ChatGPT to see if certain interactions are plausible? This could help validate or challenge the dataset's finding. Generating synthetic data points with GPT is a fascinating approach, especially for augmenting your dataset. However, measuring the quality of these data points requires some thoughtful criteria since there's no direct ground truth. Here's how you might approach it. 1. Plausibility testing. Domain expertise. One way to assess synthetic data quality is by comparing it to known interactions or consulting domain experts. This involves asking, are the generated food-drug interactions pharmacologically plausible? Do they align with existing literature or known biological mechanisms? Does the text reflect real-world mechanisms and behavior of the compounds? Using existing pharmacology databases like DrugBank or expert curation tools could help validate whether the synthetic data makes sense in the context of pharmacology. 2. Statistical similarity. You could measure how closely the synthetic data mimics the statistical properties of your real dataset. Key comparisons include distribution matching. Compare the distributions of key variables, e.g. gene expression levels, tau scores, between synthetic and real data. Techniques like Kullback-Leibler KL divergence or Wasserstein distance can be useful here to quantify how similar the two distributions are. Feature correlation. Ensure that the correlations between variables in the synthetic data are similar to those in the real data. For example, does the relationship between specific gene expression levels and drug interactions hold up in synthetic samples? 3. Noise versus signal ratio. Since your concern is about high noise error margins, evaluating the signal-to-noise ratio, SNR, can help. For synthetic data, identify signals. Look at the interactions flagged by GPT or the model as significant. Compare these to the expected relationships from real data or known interactions. Noise filtering. Apply techniques like principal component analysis, PCA, or independent component analysis, ICA, to both real and synthetic data to separate the noise components. If the synthetic data introduces too much noise, it will show in the reduced components. 4. External validation, cross-dataset comparisons. You can benchmark the synthetic data against external datasets, such as drug bank. Use known drug interactions or side effect profiles from pharmacological databases to cross-check if the synthetic data aligns with them. Clinicaltrials.gov. Cross-reference interactions identified in clinical trials to see if synthetic data produces realistic hypotheses. 5. Model performance testing. Once you've generated synthetic data, you can train predictive models on both the real and synthetic data and compare performance. Train test split. Train your model on real data and test it on synthetic data, or vice versa. If the performance drop is substantial, it suggests the synthetic data isn't representative. Transfer learning. Use models trained on real data and fine-tune them with synthetic data. If the fine-tuned models show improved generalization or robustness, this indicates that the synthetic data quality is high. 6. Uncertainty quantification. You can introduce uncertainty measurements to assess how confident your models are in the synthetic data. Low confidence predictions or wide uncertainty intervals may indicate that the synthetic data introduces ambiguity. By using these methods, you can gauge the synthetic data's quality and make sure it supports rather than undermines the analysis. Would you like to try generating some synthetic data points with GPT based on real food-drug interaction examples, or test it with models to measure performance? You're correct. Food-drug interactions are typically not the primary focus of clinical trials, and traditional pharmacology can be slow-moving and resource-intensive. Here's how food-drug interactions are generally devised outside the clinical trial context. Number 1. Text mining from literature. A significant portion of food-drug interactions are identified through text mining from scientific papers, databases, and medical literature. Automated systems scan for mentions of interactions between specific foods or bioactive compounds and drugs, extracting relevant information. This is a quick and scalable way to find potential interactions, but it's prone to errors or ambiguities in interpretation since it lacks the controlled environment of clinical trials. 2. In vitro and in silico studies. Food-drug interactions are often studied through in vitro, lab-based. Researchers use cell cultures or biochemical assays to observe how certain food compounds affect drug metabolism or activity. These are controlled studies that focus on molecular mechanisms like enzyme inhibition or transport pathways, e.g., how grapefruit affects drug metabolism through cytochrome P450 enzymes. In silico, computational. Computational models and simulations can predict how foods and drugs might interact. These models use known data about drug metabolism pathways, molecular docking, and gene expression to simulate interactions. These predictions can be based on molecular structure, known pathways like the liver's role in drug metabolism, and genetic data. 3. Metabolomics and genomics. Advances in metabolomics, the study of small molecules produced by metabolism, and genomics provide clues about how food affects drug processing. Foods can influence enzymes, transporters, or receptors involved in drug metabolism. Cytochrome P450 enzymes. Many interactions are focused on how foods like grapefruit or St. John's wort inhibit or induce these liver enzymes, altering drug bioavailability. Gene expression. Transcriptomic studies can show how exposure to certain foods or drugs affects gene expression related to drug metabolism, giving clues about potential interactions at the molecular level. 4. Case reports and observational studies. Some food-drug interactions are discovered through anecdotal evidence or observational studies. For example, patients or healthcare providers might notice unusual effects when certain foods are consumed alongside medications, like green tea affecting blood thinners. These reports can then be studied more systematically. 5. Preclinical models. In some cases, animal models are used to study food-drug interactions before human studies are attempted. While these studies provide insights into biological mechanisms, results from animals may not always directly translate to humans, particularly for complex metabolic interactions. 6. Post-market surveillance. Once a drug is on the market, interactions may be discovered through pharmacovigilance systems, where healthcare providers report adverse drug reactions. Sometimes, patterns of interaction with certain foods emerge over time, especially for widely used drugs. Why food-drug interactions aren't studied in clinical trials. Cost and complexity. Running clinical trials for all possible food-drug interactions is prohibitively expensive and complex. The sheer variety of foods, combined with differences in individual patient genetics and microbiota, makes it impractical to study every potential interaction in a controlled trial setting. Regulatory focus. Clinical trials tend to focus on the safety and efficacy of the drug itself, often under controlled dietary conditions to reduce variability. While drug interactions with other drugs are sometimes explored, food-drug interactions are often left out unless there's a known risk. Wide variability in diet. People have highly varied diets, so interactions might only affect certain populations or under specific conditions. This makes it harder to predict and study interactions systematically in clinical trials. How food-drug interactions are predicted. Given these limitations, interactions are increasingly predicted using computational methods in silico. These methods analyze known pathways for drug metabolism, e.g., enzyme inhibitors, transporters. Pharmacogenomics, to assess how food compounds might interact with genetic variations affecting drug metabolism. Network models that integrate metabolomics, genomics, and existing drug-food interaction data to predict new interactions based on shared molecular mechanisms. While these methods are faster and more scalable than traditional pharmacology, they can introduce noise, as seen in databases like food drugs. The challenge is in validating these predicted interactions, which often lack the rigorous backing of clinical trial data. Would you like to explore any of these methods in more detail, or think about how they might apply to enhancing the dataset you're working with? The food drugs database has undergone multiple updates to expand and refine the information about food drug interactions, with each version adding more text mined interactions and transcriptomic studies. However, as your hypothesis suggests, there may be noise or an error margin, particularly in interactions derived from text mining and transcriptomics. To address this, integrating error margins or confidence levels for each interaction based on the source and quality of data could provide clearer insights. Interactions identified in large scale clinical trials or validated experiments might have lower error margins, whereas those inferred through text mining could be tagged with larger margins due to ambiguity or indirect evidence. Would you want to explore assigning these confidence metrics based on the type of source, e.g., clinical data versus text mining? Or do you want to focus on cleaning up the dataset to minimize uncertainty first? From the description of the food drugs database structure, there doesn't appear to be any explicit error margin or confidence level field built into the dataset. The current tables store raw data such as text mined interactions, gene expression profiles, and similarity scores, tau values, but they don't seem to account for the quality or reliability of the interactions. The tau score in the CMAP food drugs table does provide a measure of similarity between gene expression profiles of foods and drugs, but this is a different metric and doesn't directly represent the confidence or error margin of the interaction itself. Here's what the dataset includes that could be relevant. Tau scores, CMAP food drugs. While this is useful for showing gene expression similarity, it doesn't reflect overall data quality or confidence. Text mining data, TM interactions. These interactions are extracted from documents, but there's no indication of confidence levels based on the quality of the source, e.g., PubMed articles, drug bank, etc. To add meaningful error margins or confidence levels, you would likely need to augment the dataset by 1. Incorporating external validation data. Cross-reference interactions with databases like DrugBank or clinical trial repositories to assign higher confidence to validated interactions. 2. Assigning confidence based on data source. Tagging interactions that come from more reliable sources, e.g., clinical studies or large scale trials, with smaller error margins and flagging those from less reliable sources, e.g., unverified text mining, with larger margins. 3. Using the tau score as a proxy for confidence. If you're focused on gene expression similarities, you might treat the tau score as a confidence indicator, where higher values imply stronger interactions. Would you like to build a system to infer and assign these confidence levels to the existing data? Or do you want to explore ways to further clean or refine the dataset first? Do you want to add confidence metrics directly to your dataset? Would you prefer to clean the existing data first or cross reference it with external sources for validation? Should we focus on tau scores as a proxy for interaction strength or add new error margins based on source reliability? Got it. Do you want to focus on analyzing the dataset as it is and assess the interactions with additional external tools? Or would you prefer to generate synthetic data points for comparison to see if there are noticeable discrepancies? Understood. Since the dataset has a permissive license, you don't need any external tools that would modify or assess it directly. Should we focus on developing models or algorithms that analyze and interpret the data within your application without altering the dataset? Great. Generating synthetic data and comparing it to your current dataset could help highlight patterns and discrepancies. How would you like to structure this? Would you prefer generating synthetic food-drug interactions based on known patterns, or do you want to simulate random interactions and then compare them to real data for validation? You're interested in generating synthetic data not only for food-drug interactions, but also for neural implants, EEG, and ECG recordings. This could open up new dimensions in understanding interactions, especially in biomedical contexts. We could simulate data for neural implant interactions. This could involve implant performance in relation to drug administration or other physiological data. EEG ECG recordings. You can generate synthetic EEG or ECG signals and compare these to the existing real world patterns, particularly in response to external stimuli, e.g., food or drug intake. Would you prefer to start generating synthetic signals for these biomedical recordings and then compare them to real world data? Or do you want to model specific interaction scenarios first? The current dataset you are working with, U99225024 score food drugs V2, contains several tables, each contributing to the overall understanding of food drug interactions and transcriptomic data. Here's a breakdown of the key tables and their columns. 1. TM interactions. Purpose stores food drug interaction information extracted from text mining. Columns. TM interactions ID, unique identifier for the interaction. Text ID links to the text table to show which document the interaction was extracted from. Start index and end index, index positions in the text where the interaction occurs. Food and drug, names of the food and drug involved in the interaction. 2. CMAP, purpose, contains information about the effects of compounds, drugs, or bioactives on specific cell lines, often derived from transcriptomic data. Columns. CMAP node ID, unique identifier for each node. Cell line, type of cell line used in the study. Compound, name of the compound, drug, food, or bioactive. PERT type, perturbation type, e.g., overexpression or knockdown of genes. CMAP food drugs, purpose, links food and drug interactions based on similarity scores, tau values. Columns, node ID, links to the nodes table. CMAP node ID, links to the CMAP table for compound information. Tau, similarity score, tau value, that quantifies the similarity between food and drug gene expression profiles. 4. MISC sample. Purpose, stores additional attribute value pairs for samples used in studies. Columns, sample ID, links to the sample table, attribute name and attribute value, extra information about the sample, such as environmental conditions not captured in the main table. 5. MISC study, purpose, similar to MISC sample, but for studies storing extra attributes. Columns, study ID, links to the study table. Attribute name and attribute value, additional details about the study. 6 is nodes. Purpose, links samples and node IDs for connecting different tables. Columns, node ID, unique identifier for the node. Sample ID, links to the sample table, indicating which sample the node refers to. 7. Sample, purpose, contains information about individual experimental samples. Columns, sample ID, unique identifier for each sample. Study ID, links to the study table to identify the study the sample belongs to. Treatment, describes the treatment applied, e.g. specific food or drug. Origin type and origin name, source of the sample, e.g. biopsy or primary culture. GSM, identifier for geodatasets. Time point, time at which the sample was taken. Concentration, concentration of the food or drug used in the experiment. 8. Study, purpose, contains information about the studies from which samples are derived. Columns, study ID, unique identifier for each study. Contributor, names of the people or organizations that contributed to the study. Entree ID, entree gene ID for the study. Accession, geo or other accession number. GPL, geo platform used. Title, abstract, title and abstract of the study. Study type, type of study, e.g. transcriptomics. Publication date and PubMed ID, date of publication and PubMed ID for reference. Char 9, texts, purpose, stores documents from which interactions were extracted. Columns, text ID, unique identifier for each document. Document, the text of the document. Link, URL or identifier to access the document. Citation, citation information for the document. 10. Top table, purpose, contains gene expression information used to calculate the tau score. Columns, entree ID, entree gene ID. Log FC, AVE-EXPER, log fold change and average expression for the genes. Moderated T, p-value, adjusted p-value, B, statistical values related to gene expression significance. Node ID, links to the nodes table. Gene set, identifies gene sets, such as whether they are up or down regulated. Top 150, flags the top 150 upregulated or downregulated genes. Summary. This dataset focuses primarily on interactions between foods and drugs based on text mining and gene expression data from transcriptomic studies like GEO. The tau score in CMAP food drugs provides a measure of how similar the gene expression profiles are between foods and drugs. The data has rich links between studies, samples, gene expression values, and text documents. Would you like to dive into generating synthetic data based on this structure? Or do you want to explore further how the tau scores or gene expression data can be used in your analysis? Visualizing a complex dataset like food drugs can involve different approaches depending on the specific aspect of the data you want to highlight. Here are several ways to visualize key elements of the dataset. 1. Food-drug interaction networks. Graph visualization. Since there are relationships between foods, drugs, and gene expression profiles, e.g. through tau scores, a network graph would be a natural choice. You can use a graph library like d3.js or Cytoscape to display nodes representing foods, drugs, or genes, and edges representing interactions or similarity scores. Nodes represent food, drugs, and genes. Edges represent interactions from TM interactions or tau scores from CMAP food drugs. Edge weights use tau scores as weights to show the strength of the interaction. Tool D3JS for interactive graph visualization in the browser or Cytoscape for a more detailed biological network analysis. 2. Heat maps for gene expression data. Heat map, visualize gene expression data from top table. You can map genes on one axis and experimental conditions, treatment, concentration, time point on the other. Use color gradients to represent the fold change, log FC, or expression levels, AVE-EXPER. Tool, Plotly or Seaborn Python can be used to generate interactive or static heat maps. This is useful for spotting patterns of gene upregulation or downregulation in different experimental conditions. 3. Scatterplot of tau scores. Scatterplot, to visualize the similarity between foods and drugs, plot tau scores from CMAP food drugs in a scatterplot. X-axis, food compounds. Y-axis, drugs. Color size of points represent the tau score, showing higher similarity with larger or darker points. Tool, You can use Matplotlib or Plotly to create interactive or static plots. 4. Study and sample overview. Bar or pie charts provide an overview of the studies and samples. Bar chart show the distribution of studies across different categories. Study type. Pie chart visualize the proportions of samples based on different treatments or origin types. Origin type. Plotly or Chart.js can be used for interactive browser-based visualizations. Here's a summary of visualization ideas for your dataset. 1. Network graph. Visualize the interactions between foods, drugs, and genes using a network graph. Nodes represent foods, drugs, and genes, while edges show their relationships or tau scores. 2. Heat map. Display gene expression data from top table as a heat map. Use color gradients to represent changes in gene expression, log fold change, across different treatments and conditions. 3. Scatter plot. Visualize tau scores between food and drug interactions. Use a scatter plot with foods on the x-axis, drugs on the y-axis, and the tau score represented by point size or color. 4. Bar pie charts. Provide an overview of studies or samples by using bar charts to show study types, or pie charts to represent proportions of treatments or origins. 5. Word cloud. Summarize text-mined interactions by generating a word cloud of frequently mentioned foods and drugs from the texts table. 6. Time series plot. Create line charts showing changes in treatment effects over time, using time point data from the sample table to visualize temporal trends. 7. Interactive dashboard. Combine multiple visualizations, e.g. network graph, scatter plot, heat map, into a dashboard for interactive exploration of the dataset. Each of these methods can help illustrate different aspects of the dataset, from interaction networks to gene expression patterns. Would you like to dive into one of these? For a network graph, you will need to use multiple tables to capture the relationships between food, drugs, and genes, as well as their interactions and similarities. Here's how you can map the relevant tables for constructing the graph. 1. Nodes, representing foods, drugs, and genes. Use the CMAP table for nodes like foods and drugs from compound. Cell lines or genes affected by these compounds, also captured in PERT type for types of gene perturbations. 2. Edges, representing interactions or similarities. Use the TM interactions table to create edges between foods and drugs based on text-mined interactions. Use the CMAP food drugs table to add edges between food and drug nodes, where the tau score represents the strength of the interaction. This can also be the edge weight or color. Use the nodes and top table to link gene expression data with food or drug interactions. Example, nodes. Create nodes for foods, drugs from CMAP table and genes. Edges, text-mined interactions. Link food and drug nodes from the TM interactions table. Gene expression similarities. Link foods, drugs, and gene nodes using CMAP food drugs and top table, weighted by the tau score. In summary, you'd pull data from at least 3 tables, CMAP, TM interactions, and CMAP food drugs, to construct a meaningful network graph that represents food-drug gene relationships. Would you like a sample code structure for integrating these tables into a network graph? Sure. Let's break down the process without diving into code. Overview of the visualization process. 1. Data preparation. You start with a SQL database that contains information about foods, drugs, genes, and their interactions. The goal is to convert the SQL data into a format that a browser can easily read, such as JSON. This step might be done manually or using a simple tool to query your database and export the results into a JSON file. 2. Data structure. The data needs to have two parts. Nodes. These represent the individual entities, e.g., foods, drugs, and genes. Links. These represent the relationships or interactions between the nodes, e.g., how a particular food interacts with a drug or a gene. Each interaction might have a strength value, such as the tau score, that indicates how strong or significant the interaction is. 3. Loading data into the browser. Once the data is prepared and saved in a file, like a JSON file, you need to load it into a web page. The web page will use JavaScript, specifically a library like d3.js, to load and handle the data. 4. Creating a network graph. A network graph is a visual way to represent relationships. Each entity, like a food or drug, is displayed as a node, a point or circle, and the relationships between them are shown as edges, lines connecting the nodes. The thickness of the edges can vary based on the interaction strength. For example, a stronger relationship might be represented by a thicker line, while a weaker one is shown as a thinner line. 5. Dynamic positioning and interaction. The graph doesn't have a fixed layout. The nodes move around and adjust based on the forces applied to them. This is called a force-directed layout. For example, nodes that are strongly connected will pull closer together, while weakly connected nodes might push apart. You can also add interactivity, such as hovering over nodes to see more details about a specific food, drug, or gene. 6. Displaying the graph. The graph is displayed within an SVG element on the web page, which is a type of container that allows for vector-based graphics. This means the graph can be interactive and scalable, adjusting to different screen sizes. Example workflow. 1. Export SQL data. Run SQL queries to extract the necessary data, such as which foods interact with which drugs. Save this data as a JSON file. 2. Load JSON. Use a web page, HTML with JavaScript, to load the JSON file. 3. Visualize the data. JavaScript will create the nodes, foods, drugs, genes, and draw lines between them based on the interaction data. 4. Enhance with interaction. Adjust the thickness of the lines to represent how strong or weak the interactions are, and allow users to explore the graph by interacting with the nodes. Would you like to discuss any specific part of this process in more detail, such as how to structure the data or how to set up the visualization? To convert your SQL data into JSON, we'll follow a simple process of extracting the data using SQL queries, formatting it into the JSON structure you need, and saving it as a file. Step-by-step process. 1. Extract data from SQL. You need to query the relevant tables in your SQL database, e.g. MySQL. You can do this using MySQL client tools like MySQL Workbench or a script in a language like Python or Node.js. These queries will get the nodes, foods, drugs, genes, and the relationships, links between them. Here's what you need from your tables. Nodes, from the CMAP table, which contains information on compounds like foods, drugs, and genes. Edges links, from TM interactions and CMAP food rugs tables, which show how foods interact with drugs or genes and include interaction strength like tau scores. Format the data into JSON structure. Once the data is extracted, it needs to be formatted into the JSON structure. The JSON file will have two main parts: nodes, representing foods, drugs, and genes; links, representing the relationships or interactions between the nodes. The structure would look like this: JSON nodes ID food A, group food, ed drug X, gene Y, group gene. Links, source food A, target drug X, value 2. Source drug X, target gene Y, value 4. Nodes. Each node represents a compound from CMAP, such as foods, drugs, or genes. The ED field represents the node name, e.g. the food or drug name. The group field categorizes the node, e.g. food, drug, or gene. Links. Each link connects two nodes, e.g. a food and a drug. The source and target fields indicate which two nodes are connected. The value field represents the strength of the interaction, e.g. tau score from CMAP food rugs or other interaction strength data. 3. Save data as a JSON file. After formatting the data, you can save it as a .json file. You can generate this JSON file manually or programmatically, depending on the number of records. Hack example SQL to JSON workflow. 1. Querying SQL. For nodes, e.g. from the CMAP table, SQL select CMAP node ID, compound, per type from CMAP. This gives you a list of nodes, compounds like foods, drugs, or genes. Each row can be used to create a node in the JSON structure. For links, e.g. from the CMAP food rugs table, SQL select node ID, CMAP node ID, tau from CMAP food rugs. This gives you a list of interactions, links between compounds, foods, drugs, or genes. You can format each row into a link in the JSON structure, using the tau score as the interaction strength. Number 2, formatting the data. For each row from CMAP, create a node. For each row from CMAP food rugs, create a link. Example node, JSON ID food A, group food. Example link, JSON source food A, target drug X, value 2. 3. Generate the JSON file. Once the data is formatted, you can save it into a JSON file, data.json, which can then be used in your visualization code. Storing and accessing the JSON file. Once the JSON file is generated, you can store it on your server in the project folder where it can be easily accessed by your front-end code, e.g. in a /static data/directory if you're using a static web server. The JavaScript code will then load the JSON file to build the visualization. Recap. Step 1. Query the SQL database to get the required data, nodes, and links. Step 2. Format the extracted data into JSON with nodes and links. Step 3. Save the formatted JSON into a .json file. Step 4. Load the JSON file into your d3.js visualization. Would you like further help with any of these? No. JavaScript running in the browser cannot directly interact with a SQL database for security reasons. JavaScript in the browser is client-side, and directly connecting it to a database would expose sensitive information such as database credentials, allowing anyone to manipulate or query the data. This is a huge security risk. Instead, here's how the process typically works. How to interact with SQL data from JavaScript. 1. Server-side interaction. You need a server-side application to act as a bridge between your database and the browser. This server-side application, which could be written in Python, Node.js, PHP, or any other backend language, interacts with the SQL database, queries the data, and then sends it to the front-end JavaScript via APIs or files. 2. Workflow. Step 1. The browser sends a request through JavaScript to the server. Step 2. The server queries the SQL database. Step 3. The server sends the result back to the browser as JSON XML or another format. Step 4. JavaScript in the browser uses this data for visualization or other purposes. Example flow. Using JSON. 1. JavaScript frontend makes an HTTP request to the server, usually via AJAX or fetch. 2. The server backend, which is connected to the SQL database, queries the database and formats the data as JSON. 3. The server sends the JSON data back to the JavaScript in the browser. 4. JavaScript frontend processes the data and displays it. Technologies you could use. Backend frameworks. You can use any. Sure. Here's a summary of how you can create a Flask application that interacts with your SQL database and displays data using JavaScript. Now 1. Set up a Flask application. You create a Flask web server that connects to your MySQL database. This Flask server will act as the bridge between your database and your browser. The Flask application will query the database, retrieve the data, like foods, drugs, and interactions, and convert it into JSON format. 2. Define data queries. Within Flask, you define SQL queries that retrieve nodes. These represent entities like foods, drugs, and genes from your CMAP table. Links, these represent the interactions or relationships between nodes from your TM interactions or CMAP food rugs tables. You can also include a strength value, like tau scores, to show the interaction strength. 3. Serve data as JSON. Once Flask retrieves the data from the database, it converts the data into a JSON structure that your browser can understand. You can create a Flask route like /data that provides this data as a JSON response when requested. 4. JavaScript fetches the data. On the front end, your web page, JavaScript fetches this JSON data from the Flask server. This allows your web page to retrieve the SQL data without directly connecting to the database. Sure, here are some questions to guide us through the process and clarify the next steps. 1. Database setup. Have you already set up your MySQL database with the necessary tables and data, e.g. foods, drugs, gene interactions? Do you have access to the SQL credentials, username, password, host, required to connect Flask to the database? 2. Flask backend. Are you comfortable setting up a basic Flask application, or would you like more guidance on installing Flask? Great question. If you're generating a JSON file just once, and the data doesn't need to be updated frequently, then you don't need Flask. Flask is useful if you want to dynamically query the database and serve fresh data each time the web page is loaded. However, if the data is relatively static, you can 1. Generate the JSON file once by querying your database. 2. Serve the JSON file directly from a web server or local directory. 3. Load the JSON file into your front-end JavaScript, e.g. using D3.js, without needing Flask at all. When you might need Flask. Dynamic data. If the data changes regularly, e.g. new interactions or updates in the database, Flask would allow you to always serve the latest data without regenerating the JSON manually. Complex queries. If you need to perform complex queries or calculations on the data before sending it to the front end, Flask, or any backend framework, helps manage that. When you don't need Flask. Static data. If the dataset is static or rarely updated, you can generate the JSON file once and serve it directly from your project without any backend code. Simple setup. You avoid the need to maintain a server-side application, keeping the architecture simpler. Would you like to move forward with generating the JSON manually and focusing on front-end visualization? Or do you still see a potential need for Flask if the data changes often? If you're going to generate the JSON file just once and skip the Flask application, the process will be fairly straightforward. First, you'll extract the data from your SQL database by running queries to gather the necessary information. This would include retrieving nodes like foods, drugs, and genes, and also the interactions between them, such as the strength of the interactions. Once you have the data, you will manually format it into a JSON structure that your front-end JavaScript can load and display. After formatting, you'll save the JSON file and store it in your project directory, perhaps in a location that can be easily accessed by your front-end code. This file will act as the data source for your visualizations, and since it's static, there won't be any need to regenerate it unless you have updated data. In the front end, JavaScript will load this JSON file and use it to create the interactive visualization, such as a network graph of interactions. The nodes in this graph will represent foods, drugs, and genes, while the edges, lines between the nodes, will represent the strength of the interactions. You can adjust the visual characteristics, such as the thickness of the lines, to represent the strength of these interactions more clearly. Now, let me ask a few specific questions to help us move forward. Have you already run SQL queries to extract the necessary data? Or would you like help with how to retrieve the information from your database? Is the data for the interactions, such as the tau scores, stored in the SQL tables you're using? Would you prefer to format the JSON file manually, or are you looking for a tool or script to help automate that process? Once the JSON file is ready, are you planning to store it in a specific location on your website? Or do you need guidance on where to place it so your front end code can easily access it? These questions will help clarify where you are in the process and what kind of support you need moving forward. Based on the dataset summary you provided, here are some updated questions to help guide the process of working with this data and generating the necessary JSON files for visualization. 1. Data extraction. Have you decided which specific tables will provide the information for the nodes and links? For instance, CMAP seems to contain the nodes, compounds, foods, drugs, and CMAP food drugs has the interaction strength, tau score, between them. Do you need all the nodes from the CMAP table, or are you planning to focus on a specific subset of compounds, drugs, or genes? 2. Interaction strength. Is the tau score the primary metric you'll be using to represent interaction strength between foods and drugs? Are there other metrics in the dataset that you'd like to include, such as gene expression data from the top table or interaction details from TM interactions? Should interactions with a tau score of 0 be excluded from the dataset as indicated by the changes in version food drugs v3? 3. Nodes and links. For each node, e.g., food, drug, gene, would you like to include additional details such as cell line or perturbation type from the CMAP table? Similarly, for interactions, links, should more context from TM interactions or texts be included, such as the source of the interaction, e.g., PubMed, drug bank? Do you want to represent both types of interactions in your JSON file? Text-mined interactions from TM interactions and tau score-based interactions from CMAP food rugs, or focus on one of these? 4. Data filtering. Are there any filtering criteria you'd like to apply before generating the JSON file? For example, would you want to filter the nodes and links by a certain time point, concentration, or treatment from the sample table, or by publication details from the study table? 5. Text documents and citations. Would you like to include information from the text table, such as citations or the document sources, PubMed, DrugBank, etc.? Should this data be linked to the interactions between foods and drugs? 6. JSON file format. Once the data is extracted, how detailed would you like the JSON structure to be? For example, do you want the JSON to simply include node and interaction IDs, or would you prefer to embed additional details, such as concentration, cell lines, citations? Do you envision generating multiple JSON files for different parts of the dataset, e.g., one for text-mined interactions, another for tau score-based interactions, or would you like all the data in a single JSON file? 7. Next steps. How often do you plan on updating the JSON files? Since you're generating them manually, will this be a one-time process, or will you need to periodically update them as new data becomes available? Where do you plan to store the generated JSON files, and how do you plan to serve them to the front end? Will this be done through a web server, or will you keep them locally during development? These questions aim to clarify your preferences for how the data is handled, structured, and visualized. They will guide the process of generating the JSON files from your SQL database and ensure that the end result aligns with your project's goals. Given the changes between Food Drugs v2 and Food Drugs v3, here are some updated considerations and questions. 1. Text mining interactions. The number of text-mined interactions has significantly increased. Would you like to include all the new text-mined interactions in your JSON file? If so, do you plan to include information about their sources, e.g., PubMed, clinicaltrials.gov? Are there specific interactions or sources, like PubMed versus clinicaltrials.gov, that should be prioritized or filtered? 2. Yes, it's definitely possible to turn all the data from your SQL database into a single JSON file. Since you're only doing this once, the time it takes to generate the file isn't a major concern. Here's how the process would work conceptually. 1. Extracting all data. You would run queries on all the relevant tables in your database, including TM interactions, CMAP, CMAP food rugs, texts, study, sample, MISC sample, MISC study, and top table. The data from these tables would be organized in a way that captures all nodes, e.g. foods, drugs, genes, and their interactions, e.g. tau scores, text-mined relationships, as well as any additional context, e.g. study metadata, citations, gene expressions. 2. Combining the data. All this extracted data will be combined into a structured JSON file. Each section of the file will represent different components of the dataset, such as nodes, interactions, metadata, and citations. For instance, each interaction could have references to its source from the texts table and details like gene expression from top table. 3. Saving the file. Once the data is extracted and formatted, it would be saved as a single JSON file that you can store and use for your front-end visualizations. The size of the file might be large, but since you're only doing this once, that's not a problem. 4. JSON structure. The JSON file would include nodes, all the entities, foods, drugs, genes, with their respective attributes. Links interactions, relationships between nodes, including interaction strengths like tau scores or text-mined evidence. Metadata, additional information like citations, study details, gene expressions, etc., to provide context. Would you like help planning out how the data from different tables would be combined into the JSON file? Are there any particular relationships or tables you want to prioritize when building the file, or would you prefer to include absolutely everything? If the original SQL file is just under 1 gigabyte, the size of the JSON file will likely be larger, but by how much depends on several factors. 1. Data structure overhead. JSON tends to be a bit bulkier than SQL dumps because JSON includes repeated keys, like field name value for every object, whereas SQL dumps only include the raw data. This key value format increases the size. 2. Data types. JSON stores all data as strings, numbers, or arrays, while SQL can store data more efficiently using specific types like integers or floats. This can also increase file size slightly. 3. Whitespace and formatting. JSON files might contain more whitespace, spaces, new lines, compared to SQL files, depending on how they are formatted. Removing unnecessary formatting can help reduce size. Estimation. On average, a JSON file can be around 1.5 to 2 times larger than the SQL file, depending on how verbose the data is and how much metadata you're including. If your SQL dump is just under 1 gigabyte, the JSON file could be anywhere from 1.5 gigabytes to 2 gigabytes in size, possibly more if the structure of the data adds a lot of overhead. This size is still manageable for modern systems, especially since you're generating it once. You could also consider compression, like using .gz or zip formats, if you need to reduce the file size when storing or transferring it. Does this size estimation work for you, or would you prefer a different approach, such as splitting the JSON into smaller files based on categories like food-drug interactions or gene data? Given the data structure in your SQL database, the best strategy for loading it into JavaScript efficiently would be to organize the data into a manageable, hierarchical JSON structure that maintains relationships between entities. Here's how you can approach it. Strategy overview. 1. Group and simplify data. Since your dataset contains various interconnected tables, you'll want to group similar data together to make it easier to load and traverse in JavaScript. The tables can be transformed into 3 main components: nodes, entities, foods, drugs, genes, studies, etc. Links, interactions, the relationships or interactions between these entities, e.g., food drug, gene expression changes, tau scores. Metadata, contextual data such as study details, citations, and text mining sources. 2. JSON structure for efficient loading. Organize the nodes and links into a structure that can be loaded into d3.js or similar libraries for visualizing relationships, e.g., as a network graph. The links should refer to node identifiers, making it easier to connect nodes visually. Best JSON structure. Nodes. Each node will represent an entity, like food, drug, or gene, and the attributes will include properties like the compound name, cell line, and type from the CMAP table. You can also include metadata like the source study or related citation from the study and texts tables. Links. Each link will represent an interaction or relationship between nodes, such as a food-drug interaction or gene expression link. This can come from tables like CMAP food rugs for tau scores or TM interactions for text-mined interactions. Each link will include a source, target, and interaction strength, tau or text mining confidence. Metadata. You can include additional details such as study contributors, publication dates, and citation information from study and texts. These can be either embedded in the node objects or linked separately for more efficient lookups. Specific plan for your data structure. 1. Nodes. From the CMAP table, each node would represent a compound, drug, or gene. You might store each node's ID, compound name, and other attributes such as cell line or perturbation type. The sample table can provide additional details about the source of the nodes, e.g., treatment, origin type, and you could use it to create rich node metadata. 2. Links. The CMAP food drugs table provides links between nodes, e.g., food-drug interactions, with the tau score indicating the strength of the interaction. The TM interactions table can provide additional links based on text-mined interactions, and you could assign a confidence score based on the text mining evidence. 3. Study and metadata. The study and texts tables provide valuable context that could be included as part of the node or link metadata. This will help visualize where the interactions are coming from and reference relevant studies or documents. Steps to implement. 1. Extract data from SQL. Query the SQL database to retrieve all nodes from CMAP, sample, and nodes, links from CMAP food drugs and TM interactions, and metadata from study, texts, etc. 2. Transform into JSON. Format the extracted data into a hierarchical JSON structure that groups nodes, links, and metadata. The nodes can include details like compound names and treatments, while links will contain source, target, and interaction strength. 3. Load in JavaScript. Use d3.js or another visualization library to load the JSON into JavaScript. The data can be visualized as a network graph with node sizes, colors, or link thicknesses reflecting interaction strength or types, e.g., tau scores. Questions to consider. 1. Would you prefer to create separate sections in the JSON file for different types of entities, e.g., foods, drugs, genes, or would you like to keep everything under a single node structure? 2. Do you want to include all available metadata, e.g., study information citations, in the main JSON file, or would you prefer to keep it minimal and load more details on demand, e.g., when the user clicks on a node? 3. How do you plan to manage large datasets? Would you like to load everything at once into the front end, or consider lazy loading parts of the data as needed, e.g., for very large interactions? 4. Should we focus the interactions on specific entities, like food-drug interactions only, to avoid overwhelming the visualization, or would you like all types of interactions, e.g., food-gene, drug-gene, to be included? Once we have these answers, we can refine the strategy to best suit your data and visualization needs. In the context of your dataset, tau and text mining confidence are two different metrics used to describe the strength or relevance of interactions, and both can be used to represent interaction strength in your visualization. From CMAP food drugs, tau is a similarity score used in the Connectivity Map CMAP project, which measures the correlation between gene expression profiles in response to drugs, bioactive compounds, or genetic perturbations. In your case, the tau score from the CMAP food drugs table reflects the similarity between the gene expression patterns associated with certain foods or drugs and potential interactions. Higher tau scores indicate stronger, more significant interactions or similarities between compounds, e.g., drugs or foods. Tau scores can be positive or negative, and values closer to 1 or -1 represent stronger interactions. Text mining confidence from TM interactions. Text mining confidence comes from the TM core interactions table, which stores relationships extracted from text documents, such as PubMed articles or drug bank data. This confidence score represents how confident the system is that a specific food-drug interaction exists based on the co-occurrence or contextual relationships found in the text. The confidence score may vary depending on factors like the number of references to the interaction, the quality of the sources, or the strength of the co-occurrence in the text. Differences. Tau score is based on biological data, specifically gene expression similarities, making it more robust for interactions supported by experimental data. Text mining confidence is derived from literature and provides insight into how frequently or strongly an interaction is mentioned in scientific articles or databases. Visualization usage. You could use tau scores for interactions that are based on gene expression correlations, such as food-drug or drug-gene interactions. In the network graph, thicker lines could represent higher tau scores, indicating stronger interactions. For interactions found through text mining, you could use the confidence score from text mining to determine line thickness or color, indicating how likely the interaction is based on the frequency or strength of its mention in scientific texts. Combining both. If you decide to include both tau scores and text mining confidence in your visualization, you could 1. Use different line styles to represent tau based interactions versus text mined interactions, e.g., dashed lines for text mining and solid lines for tau scores. 2. Use line thickness for tau scores and line color for text mining confidence, providing a dual representation of interaction strength. Key considerations. Would you like to visualize both tau and text-mined interactions together in the same graph? Or would you prefer to focus on one over the other? Do you want the tau scores and text mining confidence to be visually distinct in the graph, e.g., different colors or styles? Or should they be combined into a unified representation of interaction strength? These decisions will help guide the structure of the JSON file and how the data is visualized. To keep the JSON file size under 100 megabytes, you'll need to carefully manage how much data is included and how it's structured. Here are several strategies to reduce the file size while preserving the most relevant information. 1. Filter the data. Limit nodes and interactions. Focus only on the most relevant or high priority nodes and interactions. For example, you might filter out interactions with very low tau scores, close to zero, or low text mining confidence to reduce noise in the data. Remove duplicates. Ensure that nodes and interactions aren't repeated across tables. Use unique identifiers to reference the same node in different contexts. Exclude rarely used fields. Some fields in your tables, like long text fields or rarely used metadata, can add unnecessary size. You can selectively exclude certain columns, like abstract or lengthy citation text, if they don't directly contribute to the visualization. 2. Summarize interactions. Aggregate data. For example, if there are multiple studies or text mining sources that support the same interaction, summarize the interaction in a single entry. You can represent the interaction by a summary value, like the average tau score or confidence score across all studies. Simplify the metadata. Instead of including the full details for each study or citation, provide a link or reference to where the full text can be found, e.g., PubMed ID or DOI, and only store essential metadata, such as the study ID, title, or date. 3. Compress the data. Minify the JSON. Remove all unnecessary whitespace, line breaks, and indentation in the JSON file. While this doesn't reduce the actual data content, it can shrink the file size considerably by eliminating formatting overhead. Use numeric values. Replace verbose text fields with shortcodes or numeric values wherever possible. For instance, instead of storing full words like gene or food in the group field, you could use G and F to reduce file size. #4. Split the data. Divide into multiple files. If the data is still too large, consider splitting the JSON file into smaller logical chunks, e.g., separate files for food-drug interactions, drug-gene interactions, and metadata. This allows you to load only the required portions of the data at any given time. Lazy loading. Load data incrementally in the browser using JavaScript as the user interacts with the visualization, rather than loading everything at once. Number 5, compress on server and decompress in JavaScript. Server-side compression. You can serve the JSON file in a compressed format, e.g., gzip from the server, which can reduce file sizes significantly. Modern browsers can decompress this automatically on the client side, so it won't affect performance. Key questions to guide the process. 1. What data do you consider essential for the visualization? For example, are certain types of interactions, like high tau scores or high confidence text mined interactions, more important than others? 2. Would you be open to excluding certain fields or compressing metadata, e.g., citations or long text fields, if it means keeping the file size smaller? 3. Do you plan to visualize everything at once, or would you consider splitting the dataset and loading sections dynamically as needed? 4. Can you use numeric encoding or abbreviations for frequently repeated values to reduce overall size without losing essential data? Once these decisions are made, we can further tailor the strategy to minimize the JSON file size while ensuring that the important aspects of the data are retained for analysis or visualization. The most important part of visualizing your dataset is showcasing the relationships between foods, drugs, genes, and their interactions in a way that emphasizes the strength and significance of these connections. The tau score from gene expression data and the text mining confidence from literature sources are key metrics for gauging interaction strength. Therefore, the visualization should make these interaction strengths visually obvious. Using line thickness, color gradients, or varying opacity for the edges, links, connecting the nodes can help indicate stronger versus weaker interactions, guiding the viewer's attention to the most significant data points. It's equally important to make the different types of nodes, foods, drugs, and genes, visually distinct. This could be achieved through different colors, shapes, or sizes, so viewers can quickly identify and differentiate between them. Grouping similar entities or categorizing them in a way that aids navigation will also make it easier to explore the graph and understand how these nodes relate to each other. Another key feature is to ensure that the relationships, particularly the links between entities, are easy to follow. The visualization should make it clear how a particular food interacts with certain drugs, or how genes are influenced by these interactions. If a drug has several connections with different foods or genes, the network should represent this with multiple edges stemming from the drug node. This highlights the most influential entities in the network, drawing focus to their significance. To keep the dataset manageable and useful, filtering options are essential. Users should have the ability to zoom in on high-confidence interactions while excluding less significant ones. Filtering based on thresholds, such as removing links with low tau scores or low text mining confidence, helps streamline the visualization and keeps it focused on the most reliable data. This way, the visualization doesn't become cluttered, even when dealing with large data sets. Providing contextual information is also crucial. Study metadata, such as publication details, gene expression results, and source confidence, should be accessible when needed, but not overwhelm the user upfront. For example, you could implement hover features or tooltips that reveal more information when a user hovers over a node or an interaction. These could display relevant study citations, tau score details, or gene expression information, allowing users to dive deeper into the data when they want to explore specific interactions in more detail. The visualization should be interactive, allowing users to click on nodes or links to uncover additional information or follow more detailed paths in the dataset. This interactivity enables users to explore without feeling overwhelmed by too much information at once, while still having the option to access the rich context underlying each interaction when desired. By enabling zooming, filtering, and focusing on particular parts of the dataset, the visualization becomes more navigable, making it easier to uncover the significant relationships that matter most. Ultimately, the focus should be on making the interaction strengths clear, visually differentiating the types of entities, and ensuring that users can interact with and explore the data dynamically. This way, the visualization becomes a tool for both understanding high-level patterns and delving into the specifics of the interactions between foods, drugs, and genes. Feel free to dive into the data and ask any questions you may have. Whether you're curious about how specific foods interact with certain drugs, want to explore gene expression changes, or are interested in understanding the connections between various entities, your questions are welcome. The more we explore together, the more insights we can uncover. So don't hesitate to engage and share your thoughts. Let's explore this fast. Sure. Here are some quick and fun questions to spark curiosity. Which food in the dataset has the most interactions with drugs? What's the strongest interaction between a food and a drug? Can we find any surprising gene expression changes related to common foods? Which drug seems to have the widest impact on gene expression? What food-drug combo would you least expect to interact, but actually does? Which study contributed the most interactions to the dataset? What happens if we filter for only the strongest interactions? What stands out? These questions can make the exploration more engaging and help uncover interesting patterns. All the tools we're developing will be available on BioniChaos.com, where you'll find interactive applications that explore fascinating relationships between foods, drugs, genes, and more. The site is focused on making complex biomedical data accessible and fun to explore, with visualizations and interactive features that help you dive into the data without getting overwhelmed. Whether you're interested in food-drug interactions, gene expression changes, or just want to see how different compounds connect, BioniChaos.com is the place to visit. We'd love to hear your thoughts. Feel free to explore the site, try out the tools, and provide feedback. Your questions are always welcome, and we're excited to keep improving and expanding based on what you'd like to see next. Visit. Thanks for stopping by. Feel free to check out BioniChaos.com anytime and reach out with your questions. See you next time, and goodbye.